Hello everyone. A couple of administrative items before we get started. Due to the large number of attendees, we will be muting everybody's microphone during the session. You can type questions in the questions pane located in the control panel. I will answer some questions at the end of the session. Also, feel free to send us comments about the webinar or additional questions to webinars@csiamerica.com. Also, all webinars will be recorded and posted on our website. Okay, in this example, I'll talk about the different types of load patterns that can be defined, what the difference is between a load pattern and a load case. Also, I'll discuss load combinations and how they can be automatically generated in ETABS. Then I'll demonstrate how to assign unique frame and shell loading, including trapezoidal loads, non-uniform shell loads, and finally, I'll go through a detailed example demonstrating the shell uniform load sets feature in ETABS. Okay, so under the Define menu, if we take a look at load patterns, this is where we'll get started. So you can define many different loads with, these are all the different types which can be defined. And we'll go through some of the more uncommon ones here in a moment. And here is the self-weight multiplier. Self-weight of the structure is determined essentially by multiplying the weight per unit volume of each object that has structural properties times the volume of the object. So this self-weight multiplier of 1 means to include the full self-weight of the structure in the load pattern. So typically, a self-weight multiplier of 1 is specified for only one load pattern. I mean, this is usually the dead load pattern, with all of the other load patterns having a multiplier of 0, such as in this case, the live and the super dead. So be careful, if a self-weight multiplier of 1 is specified for two different load patterns, double the self-weight will be applied as a load to the structure. So that's something to be aware of. It's a common problem, especially with beginning users. Okay, so if we take a look at some of the more uncommon types of load, which can be defined here in ETABS, we have reducible live load. So reducible live load will be reduced based upon the settings defined in the design menu. Let's quickly take a look at that. So under design, you can find live load reduction factors, a few different options available to you. Tributary area based on specific codes, which are available here in the pull-down menu. User parameters based upon UBC section 1997. Defined curves as well as by stories as well. So the main difference between, say, reducible live loads and the next one, roof live loads. So roof live loads are not automatically reduced by the program. So you'd have to put in the values in manually yourself. Next on the list, we have notional loads. It's a lateral load based upon another vertical load pattern. And this can be applied automatically or manually when the lateral load entry is set to 0. So if we just define one of these and click on auto, you can see it can be based upon a specific base load pattern, enter a load ratio, and it can be in the X or Y direction. Or, as I stated before, you could enter it in manually if this is set to none. A few other ones here. Of course, we can define seismic loads, wind loads. We have all these different auto lateral load codes that have been embedded here in ETABS to choose from, where you can select one of these. And you can define all the different lateral load directions, eccentricities, time period, story range, and the coefficients can all be defined here as well. Now, this can be done for not only seismic, but wind loads as well. Another unique load pattern type, seismic drift. So this is very similar to seismic, of course, but the same code options are available as defined for the seismic load type. But this option does not enforce certain upper limits on the period, resulting in a lower base shear and deflections when checking drift limits. So these are some of the differences between these load types. So once we have, I'm going to delete a couple of these. Once we have a couple load patterns defined, we'll leave the self-weight, live, and super dead for this example. Let's go and talk about the load cases. So that can be found underneath the define menu as well, under define load case. One other note I wanted to discuss about load patterns. So if multiple loads exist for a specific load type, say in case for dead load, say you have an equipment load, cladding dead load, or self-weight dead load, each of these loads must be given a unique name. Also, each of these loads will be included in the automatically generated load combinations, which I'll talk about here shortly. Okay, now going down to load cases, let's talk about this for a second. So when you have a load case, the common question is, what are the differences between a load case and load pattern? So a load pattern by itself does not create any response, such as deflections or stresses, for example. A load case must be defined to actually apply the load to the structure. So every time a new load pattern is defined, the program automatically creates a corresponding linear static load case with the same name. So in this case, it's going to be self-weight, linear static. We can take a look at how this is defined. So for a new model, the program creates a default load pattern called dead, or in this case, self-weight, which applies the self-weight to the structure. So if we go through some of these load case types, so we have by default linear static, non-linear static, stage construction. Now, once I select each one of these, you'll see that the form changes with different options which become available. And in other webinars, I've discussed response spectrum, time history, but for today we're going to keep things pretty simple and keep to linear static. We could define a specific mass source. There's some P delta nonlinear stiffness options, and you can select the specific loads applied in a load pattern or acceleration. For this case, I'm just going to stick with the self-weight of the structure. So now I'll just get rid of a couple of these. So we have, because we defined the load pattern of self-weight, live, and super dead, those corresponding load cases have now been defined as well automatically. All right, so under the define menu, let's take a look at load combinations. Let me just delete all these and start from scratch. Okay, so in ETABS, load combinations or combos are generated automatically by the program or can be user defined. So if the automatically generated load combos are acceptable, no definition of additional load combinations are required. So what we can do here is add a new combo, and we can add them manually if we like. We'll touch upon this here in a minute. But we have a tool in ETABS called Add Default Design Combos. So this will add combinations in accordance with the code selected in the design menu. I'll show you that here in a minute. So once you select, say, perhaps the steel frame design code for the steel frame building, it recognizes that I've defined the self-weight, alive, and in this case, the super dead, and will generate combinations for me automatically. So if I click OK, it will generate some combinations. I can put the cursor over the combination itself, and it will tell me what is defined. So in this case, it has a combo of self-weight, live, and super dead, all with a scale factor of 1 associated with it. So I don't necessarily have to click on Modify Show to get the information. I can simply put the cursor over the combination itself to get the information I need. Okay, so here are some default combinations. You don't necessarily have to use those. We can go ahead and add new combos ourselves. So let's take a look at all the different options which are available to the user. So the first option is linear additive. This is the most common one. Simply an algebraic linear combination of the maximum values for each of the included analysis cases. So if I wanted to add a self-weight of 1, live load as well, and I could create any different combo based upon the load patterns which are defined. We also have envelope, which is the maximum of all the maximum or minimum values for each of the included analysis cases. So that will give a maximum or minimum value as well. SRSS, a square root, sum of the squares of the larger absolute values of the included analysis cases. And lastly, there's range additive. So this is the sum of the positive maximum values for each of the continuing cases, or excuse me, contributing cases. This combo type is useful for pattern or skip loading, where all permutations of the contributing load cases must be considered. So for this example, we'll just stick with a linear additive. Quick note about combinations. Let me just show you. I click OK here, and we go to Design, Steel Frame Design, and select Design Combos. So here in this menu, the combinations must be used to select the user-defined combos in the design. So I need to select them and move them from the list of combinations to the actual design combos. So whether combos were created manually or created by the default combo option, you still need to bring them over here for ETABS to use them in design. So note that each time a design is run, the automatic combos are regenerated, therefore replacing any previous automatic combos, but the user-defined ones are not changed during design. So this is an important step to actually select the list of combinations to be used in design. This can be found underneath the Design, Steel Frame Design, and then Design Combination Selection. So because this is a steel frame structure, under Design, Steel Frame Design, this is where you actually select the code. And based upon this code, in accordance with this code, the design combinations are generated automatically. Okay. Why don't we talk about some frame loading options here. Right now I've pulled up, I'll zoom in a little bit here, I pulled up an elevation with some steel frames as well as bracing, beams and columns. And underneath, I'll select a couple of these braces first. And what I'm going to do is talk about the different options available for frame distributed loads. So this can be found underneath the Assign, Frame Loads, Distributed. Okay, the load type and directions can be defined. These are all the different options available. Local 1, 2, and 3, pretty obvious to understand how those are applied. There's typically some questions for not only gravity, but gravity projection as well. What does that exactly mean when I use these options in ETABS? I'm just going to quickly pull up the help menu to help us understand a little bit. So here in figure A, this line load, distributed load W, is applied to a frame object in the gravity projection direction. Okay, this is how the load is going to be applied, and it's shown graphically here. The other option is with the force W, with the cosine theta acts along the entire length of the object in the gravity direction. So it's important to note that gravity is downward in the negative global z direction. Okay, so I'm going to apply a load using each one of these options. I'll put in, say, 20 kips. Oops, let's delete this one here. Okay, so that's for the gravity direction. And now I'll click on gravity projection, and I'll apply that same 20 kip load. But now, one more time, need to select the brace first and apply. All right, so now I'll go to display just to see all the loads being shown on the screen simultaneously. I'll click on display, load assigns, frame. Now you'll notice for the gravity projection, it's showing the actual value of 20 kips per foot. This one is going to be including the cosine theta value, which has been multiplied by 20, therefore having a value of 17.432. So that is how the loads are being applied in those two different scenarios. Now, if we talk about going back to that same dialog box, we can go to frame loads distributed. This time, let's talk about trapezoidal loads and how this form can be understood. So going back to the ETABS menu help page here, this is a very detailed graphic which exactly explains how trapezoidal loads can be applied in ETABS. So we have a situation here where I can apply the load as a distance or as an absolute distance or a percentage of the distance of the frame itself. So in this case, at the quarter point, this load will be applied as 1 kip per foot, and at the halfway point, at 0.5, the same value can be added. And this is how the load distribution is going to be shown on the beam itself. Now you'll notice once the load distance is set to 1, all the values after that will be disregarded. So in this case, it starts at 0 and it goes to 1 at distance of 100%. So once you've entered a distance of 1, any value after that is not going to be read, as you can see in this situation down here as well. So I can add third points, 2/3 points, quarter points, anywhere I want to create different scenarios for trapezoidal loads. So going back to this example, I'll delete the uniform load and say I wanted to put a load at the quarter point of 10 and same at the 3/4 point. Now if I click apply and zoom in here, you can see how these trapezoidal loads have been applied to the beam very easily. All right, some other unique loading criteria that can be applied in ETABS. We have the assignment of non-uniform shells. So let me just open up the plan view here. And we'll go to the, I think the parking level works out well. So this can be used for any shell. It could be used for, in this case, a floor element, a wall element can be used as well. So if I go to assign shell loads non-uniform, let me show you how to read this dialog box. So essentially, you can define shell loads that can vary linearly in each gradient. So in this case, A indicates how much of the magnitude of the load changes per unit of distance parallel to the x-axis. So B is similar, indicates the magnitude of load change per unit distance parallel to the y-axis, and C being the z-axis. Now D is a little different. D is the actual magnitude of the shell load. So in this case, we'll keep it 20 pounds per square foot. And I've selected the shells. You can see in the bottom left-hand corner of the screen, kind of a bookkeeping system. It tells me exactly what I've selected prior to performing an action on it. In this case, applying a non-uniform shell assignment. I'll click apply. So essentially this is showing a graphic saying A, B, C, D, what the values are, but there's a little nicer way to view this. We can take a look at it graphically in a contour format. So to access that, I'll click on Display, Load Assigns, Shell. And I can click on the contour plan view, the specific direction that has been defined, and I can click Apply. Okay, so now I have non-uniform shell assignments, and I can simply put the cursor over the shell itself to get the magnitude of the load that has been assigned. So this saves the user lots of time. In previous versions of ETABS, the only way you could have done this was to break the shell into pieces and individually assigning a shell load to each one of those pieces. So that is not the case anymore, as you can see. How the load changes as I move across the screen here. Again, this can be used for shells and or wall elements as well. Just a quick note when I'm talking about shell elements. So there's the use of a none property. And let me show you what I mean about that. So I'm just going to click on an area object here and draw it. Now I'm selecting a none property. What does that mean? It's an area object used to apply area loads with objects without contributing to the structural stiffness. So if you have a situation where you have an equipment load, perhaps, you have some sort of unique loading in just a unique or a specific section of a slab, you can apply a none area object property. And I can apply a load directly to this area object, and just the load will be applied to the structure. The none property has 0 structural stiffness, so it will not change the structural integrity of the analysis model. So I can simply select this area object, assign shell loads, and I could use any of the options I've discussed before. Uniform, non-uniform. This can be applied directly to this none area object as well. And why don't I just assign a uniform load to it just to show you. There's your 20 kips per square foot. Okay. I'm going to bring up another model here to discuss the use of shell uniform load sets. And let me tell you about that. It's a very useful feature here in ETABS. I'll bring up this model. So under define, you'll find this underneath the define menu, shell uniform load sets. Now, what does that mean? So a shell uniform load sets, they're essentially intended to assign loads based upon a type of occupancy. So in this case, I've decided there's hallway loading, as you can see right here, and office space loading. So such load sets may consist of several different load patterns, including dead, super dead, and live loads. So essentially, it's kind of a shortcut. I can define all of these different load patterns in a single load set. So in this case, for hallway, I can click on Modify Show Set. Now in this hallway uniform load set, there's a dead load, which is just a self weight, a super dead load of 30 pounds per square foot, and a live load of 100 pounds per square foot. Now this is all in one load set. What I can do is assign that load set to a specific shell element. And I'll do that here in a second. Let me just show you how the office load set has been defined. Very similar, but for hallways, if we just have different super dead load values, 10 pounds per square foot, and a live load of 40 pounds per square foot. Okay, so what I'm going to do here is I'll select the office area objects, and I can go to Assign, Shell Loads, Uniform Load Sets, and I'll click on this case Office. Okay, and it's actually already been done. I can do the same thing for hallway, which has actually already been done. Okay, so what does that mean? So essentially I can right click on the office area object, take a look at the loads, and you can see that this office load set has been assigned, and I already showed you exactly what that meant about the 3 different loads that have been applied in that. So this saves the user quite a bit of time. He doesn't have to go in and individually assign the dead, live, super dead loads directly to the objects themselves. Now, say you have a very large structure, 10, 20 stories, I could just simply go back to the define shell uniform sets definition here. And if there are any changes made to it, I can make the changes here directly, and all the changes will be made automatically to any area object that has the office shell load set applied to it. Okay, so let's run an analysis and take a look at some output. Okay, so if I go to display forces, stresses, shell forces, and stresses, we can take a look at a moment maximum. We'll take a look at on the deformed shape, and click apply. Okay, so let's take that. So I'm looking at the dead load, which is uniform everywhere. Let's take a look at this in 3D. I guess it doesn't matter. Dead load, which is uniform. Now you'll see that here's the live load, which is different, and the super dead as well. So you can step through each one of the different load patterns individually, dead, live, super dead, and take a look at how the values change. Okay. Why don't we take a look at some questions now? Okay. Okay, how will earth pressure be put on ETABS in a retaining wall? So that essentially can be done using the non-uniform load application in ETABS that I talked about before. So essentially what I've done here, if I take a look at this in 3D, so what I've done before is select an area object, which was a slab, but you could do the same thing for walls and or retaining walls as well. I can go to Assign Shell Loads, Non-Uniform, and set these parameters A, B, C, and D to apply earth pressure on a retaining wall in ETABS as well. So that's the way to do that. Yes, there's a question about is there a code-mandated numerical limitation on reducible live loads? Will ETABS take that limit into account when calculating? Yes, when I talked about that menu under the design menu here, live load reduction factors, you can select how ETABS is going to reduce based upon the code, and here's where you select that code-mandated limitation. So this will take all these code limitations into account in reducing the live load, which is done in the design of ETABS. So there's a question, is the load on, when we talked about the none area object, let's bring that up again here in plan view, is the none, where'd it go? All right. Is the load on the none element added to the load on the shell element below? That is correct. So if I click apply, you'll notice that this is a none area object. It will be applied directly to that shell that has been applied to. So these two none objects, both with 20 pounds per square foot, are going to be applied directly to the shell. And then of course, the shell will be meshed and the loads will be distributed to these beams and columns here, just to the left and right of it. Okay, so this question's about, we'll go back to the combinations here. And talk about excuse me. Okay. So it says uniform load sets have not exported to safe. Is this a problem that exists now? I have to check on that for you. I think exporting to safe shell uniform sets is an option. If it was an issue in the past, I'm sure it'll be rectified here shortly. But yes, there should be no issues exporting from ETABS to safe and having the shell uniform load sets to be included as well. Okay, that's all the questions here for now. Again, if you have any further comments or questions, please feel free to email me at webinars@csiamerica.com. Thank you very much for joining me here today. Please look at our website for future webinars listed, and we will see you all very soon. Thank you very much.